Hello, Earth Science. So here's the continuation, even I should say the conclusion of section 1 of chapter 22. We're going to do the layers of the atmosphere. So, of course, the atmosphere is something that you're going to find on the surface. So let me go ahead and just draw some ground. And I'll put a mountain in there. And there we go. Alright, so we've got surface. Here, let me adjust that, make that a little bit more even. There we go. Principle of original horizontality and all that. So now that we've got the ground, we are at an altitude of 0. We're going to be doing kilometers because, of course, this is all coming from a science book, so all the numbers are in kilometers. So you know what the air is like at the ground. Today it was pretty nice. We're doing this in the springtime, so the temperature is fairly high, at least as far as the rest of the atmosphere goes. It's fairly warm. Now, here's a nice puzzle for you. The sun is that way. As you go up high, it gets colder, but you're getting closer to the sun. Why does going closer to the sun make it colder? Just something for you to think about. Maybe the answer will occur to you during the lesson today. Anyway, as you go higher, the temperature does decrease. So here's what I'm going to do. I'm going to have a temperature scale so that on the right, here, let me make that be in red. That's the international color of high temperature. Oops. So we'll put hot over here. And of course blue is the cold color. So around here the air is pretty cold. So let us get an idea about an elevation. If the ground is 0 kilometers, I'm going to go ahead and just draw a dotted line at 11 kilometers. Okay, so 11 kilometers is pretty high up, and at 11 kilometers we have something that is called the tropopause. Now, underneath the tropopause, the region of the atmosphere that is closest to the ground, we have the troposphere. So the troposphere is the region of the atmosphere all the way up to 11 kilometers, and the trend of the temperature in the troposphere is that it starts out fairly warm at the ground, but the higher up you go, the further it goes to the cold side. So up at 11 kilometers height, it's very, very cold. Now, down in the troposphere, this is where basically all the clouds are, or I shouldn't say all the clouds, it's where most of the clouds are. It's where most of the weather is. This is, of all the things that interact with us on the ground, where most of the things in the atmosphere are. So we've got a tropopause at 11 kilometers, and past 11 kilometers we've got another region, and that region is called the stratosphere. The stratosphere extends quite far. It extends all the way up to I'm going to try to make this to scale. I'm not sure if I can. 10, 23. Oh, yeah, not quite to scale. I'm going to try though. Okay, so the stratosphere extends all the way up to 50 kilometers. 50 kilometers, and at the top of the stratosphere, that boundary is called the Stratopause. So I think at this point you can probably get the pattern. There is the something sphere, and then the top of it is called the something pause, right? So let's talk about the stratosphere for a second. When we left off at the tropopause, the temperature had been decreasing. It turns out that the temperature increases from this point on. So we have, let me get this as precisely as I can. The temperature, as you go up, increases. Not as much as it was down at the ground, but the higher up you go in the stratosphere, the warmer the air gets. Why is that? So there is a particular gas that is part of the atmosphere in a very low concentration, but it exists in one particular place, and that would be ozone. So this is where the ozone layer is. And the reason that the atmosphere warms up in the stratosphere is because of ozone's special property, that is, that ozone absorbs ultraviolet. Since ozone absorbs ultraviolet, it means that the energy in ultraviolet light goes into the ozone itself, and when atoms absorb energy, they heat up. So the reason that the stratosphere warms up is because it absorbs ultraviolet light. Okay, so that's the stratosphere. It ends at the stratopause. Let's scroll down. Scroll up. All right. So above the stratopause, the region of the atmosphere there is called the Mesosphere. And the Mesosphere extends from 50 to 80 kilometers up. So the top of the Mesosphere is it's about 30 kilometers higher than the stratopause. You want to guess what it's called? Obviously, can't really do a call and response here, so I'll have to tell you, but you probably know. If the top of the stratosphere is called the stratopause and the top of the troposphere is called the tropopause, then the top of the mesosphere is called the mesopause. And that is at a height of 80 kilometers. And in the mesosphere, the temperature goes back down, drops with elevation. Now, it's worth noting at this point, air pressure is extremely low. The air is very, very thin, and it turns out, in fact, that 99.9% of the air is actually below the stratopause. So we barely have any air left up here. Okay, so I just want to go back down to the ground for a second so I can catch us up to where we are, and then we'll move on. Down to the ground. Okay, so we're on the ground. Air temperature is high. Why is the air temperature high down here? It's because when the sun shines on the surface, it warms up the surface. That warms up the air, and the air holds that heat close to the surface. The further up you get, the further away from the surface as you are, and the less you're warmed up by it. Because the sunlight just kind of passes straight through the air. It doesn't warm up the air, it warms up the ground. The ground is warming up the air. The only time that the sunlight actually warms up the air is out of the troposphere, past the tropopause, up into the stratosphere in the ozone layer. The ozone layer is where light actually is warming up the air because it's absorbing the ultraviolet. So the temperature goes up in the stratosphere up until the stratopause at 50 kilometers height, at which point we've reached the mesosphere, and 99.9% of the air in the atmosphere is below us. Past the stratopause, we enter into the mesosphere. The mesosphere gets colder as the height goes up, and the top of it is called the mesopause. Now, I do want to point out, it got cold down at the top of the troposphere, at the tropopause, but this is where it gets really cold. The temperatures around here can be around negative 90 degrees Celsius. That is brutally, bitterly cold. But also, you know, there's not a lot of air to breathe, so you can basically choose how it will kill you. Okay, so we've got some atmosphere to go, so let's go. We got our mesopause that we've identified, and above the mesopause, that is the atmosphere, the layer of the atmosphere above the mesosphere, is called the thermosphere. I will not be able to draw this one to scale because this one goes from 80 to 500 kilometers. So for all intents and purposes, this is the top layer of the atmosphere. And the thermosphere, let me write that name actually. Let's see, I haven't used this one. You may recognize thermo as meaning heat. So the thermosphere is the fourth layer of the atmosphere. As I said, it goes from 80 to 500 kilometers, and with this, the temperature again increases with elevation. Okay, so why is a thermosphere so hot? So back down in the ozone layer, the reason that the air was warming up was because it was absorbing ultraviolet radiation. When you absorb radiation, you take on heat. So up here in the thermosphere, we must be increasing temperature because of the same thing, absorbing radiation. So what kind of radiation are we absorbing? In this case, it's stuff like X-rays, also some ultraviolet radiation. So the thing is that this layer of the atmosphere, let me write this down, this layer of the atmosphere, this takes the brunt of solar radiation. That's why it heats up. It's absorbing X-rays, it's absorbing ultraviolet. Look, the sun is a sustained thermonuclear explosion. It's releasing lots and lots of radiation. A lot of it is deadly. And the only reason that it can't kill us here on the ground is because it had to go through miles and miles of atmosphere. And up here in the thermosphere, that is the front lines of that shield. So that's where most of the energy absorption is, and so that's where most of the heat increase is. In fact, the temperatures up here can get so hot, they can get all the way up to around 2,000 degrees Celsius. If you remember, way back when we were doing magma, that's the temperature of mafic magma. It's very, very hot. So, do things burn if they go up that high? As a matter of fact, they don't. If you were to go up to that height, it wouldn't feel hot to you. How is that possible? Right, so do you remember the kinetic theory of gases from the first part of this section when we were talking about how when atoms warm up, they move faster? Basically, 2000 degrees Celsius just means that the air molecules up there are going really, really fast. In order to heat you up, a whole bunch of them would need to hit you. When there's not a lot of them, they can't contribute all of their energy to you, thus heating you up. So it doesn't feel very hot, even though it is. Okay, so since we're up to 500 kilometers, and we're kind of technically in the atmosphere, you might think, okay, so where's space? That's actually kind of funny. There's not really a line. Where are we going to draw the line between the atmosphere and out of the atmosphere when it keeps just getting thinner and thinner? Here's a good example. The International Space Station is actually in the thermosphere. Its altitude is only about 400 kilometers, and the thermosphere goes up to 500. So, is the International Space Station actually a space station when it's in the thermosphere? So there are various ways to try to define where space starts. There's one particular definition that I rather like. It's not like I'm an authority on the subject, but let me tell you one way to define where space is. You know how airplanes work with an airfoil. The wing has to get lift by moving through the air. When the air gets thinner, the wings are less effective. Space can be defined to start where airplane wings are less effective at keeping you airborne than rocket engines. As soon as you can't use a wing, but you can use a rocket to be in orbit, that's one way to say you must be in space then. And that would be within the thermosphere, because obviously that's what the International Space Station is doing. Okay, that's also where a lot of the other satellites are, like artificial satellites. Right, so there are a couple other things that end in sphere that aren't technically, I don't know that you'd want to call these atmosphere, but I'm going to go ahead and just name them for you. I'm going to move this down and kind of write them up in the top of the list. So the first one is called the ionosphere. So the ionosphere is made of layers of ions that are formed from gas molecules broken apart by solar radiation. Okay, so basically these are all the broken atoms from solar radiation. So it's kind of funny because that means if atoms are broken, it means that there are positively charged pieces, negatively charged pieces. And so we almost have like I almost want to call it like an electrical force field around the planet from that. And it's kind of funny because since they're electrical, they'll actually interact with radio waves. You can actually reflect AM radio waves off of the ionosphere. And that means that in some places, just by that coincidence, you're actually able to get radio stations from really far away, like hundreds of miles away, just because they bounced off the atmosphere. Okay, there is one more thing ending in sphere that's worth mentioning. It is called the, shouldn't have put a space in there. Pretend that's not there. The exosphere. And the exosphere, you could say, is like the extreme upper layer. There's really not even a height description. Depending on how you want to categorize it, even the moon is in the exosphere. But things in the exosphere would be stuff like hydrogen and helium, really, really light gases that are basically just floating in space, not even really in the air. It's basically nothing. and there's no definable boundary. So, it's a poorly defined region. It's basically just everything past 500 kilometers, who knows where it ends. It just fades into oblivion. Anyway, let's just take a quick recap of this whole atmosphere, and then we will be done. So let's just drop back down to the ground. Boom. Oh, that hurt. Get it? Because we fell down. Okay, so there's the ground. We're in the troposphere. The temperature is high, but the higher we go, the further down the temperature drops until we're actually very cold at the tropopause, at the top of the troposphere. But as we go above the tropopause into the stratosphere, the temperature tends to rise again because of the absorption of ultraviolet in the ozone layer. So when we get to the stratopause at 50 kilometers, it's actually quite warm, but there's 99.9% of the air below us. The atmosphere up here is extremely thin. In the mesosphere, the temperature decreases all the way down to negative 90 degrees Celsius, and we top off at the mesopause. So above the mesopause, we are in the thermosphere, which takes the brunt of solar radiation, so the temperature increases dramatically to 2000 degrees Celsius, even though it doesn't feel very hot because the air is so thin. And up here is where we have stuff like the ionosphere, because the atoms have been ionized due to their exposure to radiation. And past 500 kilometers, we might as well just call it the exosphere, which is just an atmospheric term for basically no air anymore. Okay, well, that is the atmosphere, its regions, and its characteristics. There's not much else to say about that, so I'm going to err on the side of caution and just stop it here. Get it? Air.